I'm Edward Tell, I'm the team leader. I'm joined by Paul Shipley, Victoria Hathaway, and Jose Benacourt. Our advisor is Lance Viandel of the ECE department, and our customer is Guy Pommel of the UMass Dartmouth Fitness Center. So our project is the dot drill system. What the dot drill is a mat that is used in a gym setting that consists of 5 dots, 5 inches in diameter, placed 3 feet edge to edge from top to bottom, 2 feet edge to edge from left to right. The total size of the mat is 3 foot by 4 foot. This is our mat here on the floor, which we will demonstrate for you guys later on in the presentation. So the idea of the dot drill is to give you a mathematical statistic on how well you're able to do an agility training situation. So there's predefined patterns that you have to perform in, which have been defined as a standard for the dot drill. This is the dot drill standard as well, which we conform our board to. So I'll hand it over to Paul Shipley.
So when we first started this project, we started out by going through our system requirements, and we did this by first getting what our customer wanted, which were our customer requirements. Then we used those to derive our engineering requirements, which were what we wanted to do to help meet those. And then lastly, we just wanted to make sure that everything fit our constraints and standards by dot drill and by the IEEE. So first was the customer requirements, which was that the mat, most importantly, had to be lighter and be more portable to carry for one person. Because it's going to be used in a gym and one person might want to use it or move it somewhere else, that was important for us. Secondly, we wanted to make sure that the system was wireless. Not only did this also make the system easier to carry, but when it's in a gym and a lot of people are moving around, wires could be possibly a safety issue. So we just wanted to eliminate that. And then we also needed to make sure that, like we said before, the platform consisted of 5 circles, which are the dot drill pattern. Going off of there, we wanted to make sure that the athlete could complete the pattern accurately and effectively, and that we could assess that performance. And then lastly, that there could be a countdown to notify the athlete when to begin the actual drill itself. So for our engineering requirements derived from those, firstly, to make sure it's lighter, we measured the previous year's board. When we measured this board, because it's made out of plywood, we found that it was 34 pounds, which was extremely heavy to carry, and it was kind of a pain. So for our first requirement, we decided that no matter what happened, we would have to make sure that our mat was going to be lighter than last year's mat. Next, for the wireless communication, well, we wanted to make sure that this actually did make the mat easier to use, and not that if the wireless communication was unreliable, if that would hinder performance or accuracy of the design. For our third requirement, the platform had to still consist of 5 dots. We just cross-referenced these with the other dot drills that are already in existence. So we just need to make sure that those were all 5-inch dots and that they were all by the correct dimensions. For our fourth requirement, which was the accuracy, we broke this up into 3 different things. First, we wanted to make sure that the actual movement was recorded accurately. So if you step on a dot, it's recorded as a hit. If you don't, even if you're very, very close, we wanted to make sure that that still wasn't picked up as an actual activation. Next, for the timing for the user's activity, we wanted to make sure that the timing was as accurate as possible. This comes into play later with the 5th requirement, which is the 3-second countdown. And then lastly, for accuracy, we wanted to make sure that we had a scoring system to try to give the user a better idea of how well they actually perform the drill. We did this by measuring the time that it takes them to finish the drill and the amount of misses that they make. And from those 2 scores, we kind of make a weighted time based on how many that they've missed, which adds a second for each time they miss. And then lastly, to notify the athlete of when to begin the signal, we have a 3-second counter and then a go-up timer, which you'll hear later when we actually demonstrate the mat. For constraints and standards, start off with the correct dimensions of the dot drill itself. 5 dots, 5 inches across in an X pattern, and the correct width and length. We follow the IEEE Code of Ethics, was to make sure that the mat itself wasn't going to hurt anybody or it's safe to use and it's not going to damage any property. And then lastly, we have to follow Bluetooth 6 standards, which are put in place by Bluetooth SIG, who designed Bluetooth wireless communication, and we did this by using the MIT App Inventor and their built-in functions to make sure that it reliably communicated.
Our system begins with us designing it so this way the user can be self-sufficient. So what we have is we have the graphical user interface to help the user interact with the electrical aspects of the system. They interact wirelessly with the embedded microcontroller where the processing takes place. So the embedded microcontroller will receive and send commands back into the user. So typically the user would send a command choosing one of the various training drills, and based on that command, the embedded microcontroller will respond back, letting the user know that they can begin the drill. The user will then be able to use the sensors, which are on the map underneath the circles, and the sensors will indicate whether or not the user actually hit or missed the buttons. The wireless communication and embedded microcontroller also required a separate power supply, wireless, since it was a separate system from the tablet. Next, we have our design concept. Here we evaluated several design alternatives for two of our subsystems. Our first subsystem was wireless communication, and our second subsystem was the sensor. The design and we'll cover also the design rationale of the final design concept. So for evaluating the design alternatives, what we chose was Bluetooth and Wi-Fi network for the wireless communication. And then for the sensor, we chose dielectric material, momentary push button, and transponders to review. For the wireless communication, after analysis, we discovered that the Bluetooth was low in power, cost, as well as risk of interference. Whereas the Wi-Fi network was easy to implement, had a high bandwidth, and connected to several devices. For the purpose of our design, we didn't feel like that was an issue. So for subsystem 2, for the sensor, we have the dielectric material, which is a lightweight, flexible fabric. We have the momentary push button, which is just a mechanical mechanism, and then we have the transponders. For the dielectric material, it would be a circular piece of fabric, and you could indicate exactly where within the button it was pressed. So that was gave us a high precise actuation, whereas the momentary push button and the transponders lacked in that department. So for overall, for the design rationale, we ended up going with Bluetooth for the wireless communication because of the low power, low cost, and low risk of interference. For the sensor, we chose the dielectric material because it was lightweight, flexible, had high durability, and high precise actuation.
For our technical design, we broke it down into a few subsystems, including the power system, the GUI, which is on our application, then the wireless communicating between them, which we use as Bluetooth, and our embedded system of a 228p microcontroller. So our first system is our sensors. So our sensors are made up of two pieces of conductive fabric sandwiched with a dielectric material in between them. So as you squish this material, it changes in resistance. So connecting from these sensors to our processor, we use a copper tape, which has two conductors to connect the two together. Using Kirchhoff's law, we're able to take the unknown resistance, which is our dielectric material and our buttons, over a known resistance and known voltage. We're able to determine when and which buttons are being pressed at any given moment. Our map, which is shown on both, is a sandwich of two large pieces of rubber flooring that came custom from the gym itself. So these are one piece with our sensors in between them sandwiched down. On top are five 5-inch circles cut out of vinyl to indicate where our 5 dots are for the dot drill system itself. We have a graphical user interface that is located on a tablet that was provided for us by the previous year, my customer. So this application allows you to connect the Bluetooth standing at the top to the mat itself, which we use a HC05 Bluetooth module on the hardware side to communicate. We give you a weighted time average after. This is based on how many misses you have or extra dots that you hit during the drill itself. And then we'll also give you that incorrect number that you missed on the drill. The weighted time average is based on how long you did it and then multiplied by a variable of whatever can be set by the gym itself. We have it currently set to just 1 second penalty for every miss or extra hit that you actuate. So right below that, we have a start drill button to begin the drill. Below that is a drop-down list, which allows you to select between the 5 drills that we have currently located in there. The dot drill mainly consists of one large drill that is 4 drills combined together. So we allow you to practice each one of those smaller drills individually, get you a better training on before you're able to do the larger drill. So once you select that drop down, you are greeted with a message that tells you instructions on how to do the actual drill itself, as well as an image below mapping out the order to go in. On the right side of the screen, we also have a high score system. You want a lowest number for the drill, because the lowest time average is better in this situation. So our schematic of our components are here. Our processor is an Atmel 328P. Use this because of its ease and small footprint, as well as serial communication. So connecting from our processor, we use a HC05 Bluetooth module to communicate with the tablet application here. Our power system is an Adafruit Power Boost 1000. This allows us to both charge from an external source of a 5-volt wall wart to charge a LiPo battery. And then that LiPo battery is then regulated by the Power Boost down to the 5 volts that we need for the actual drill itself. We were able to calculate out at a runtime with the battery provided a 10-hour at full use or 14 hours at standby, which was plenty time for a dot drill to be used between charging cycles. So, turn over to Tesla.
We ran a few test plans to make sure that the requirements were all met. The first requirement was to make sure that the current mat weighs lighter than the previous one, which weighed at 34 pounds. The verification method we used is the analysis method by weighing the current mat, which weighs 22 pounds, which is indeed lighter than the previous one, and it's also flexible, which makes it easier for transportation. The second requirement was to make sure that the platform can communicate wirelessly with a success rate of at least 90% at a 10 meters distance with the graphical user interface. The verification method we used was analysis and test. We measured 10 meters, and the application successfully sent a received message from the Bluetooth module. The third requirement was to make sure that the circles, that there were 5 circles on the mat, and that they were each 5 inches in diameter. The verification method we used was inspection and analysis. We measured each of the circles, and they were 5 inches in diameter. The fourth requirement was user's accuracy input. The system must record the user's movement, full movement. The verification method we used was testing. We used a stopwatch against the dot drill mat, yield the time difference of 1.3 seconds, which is within the margin of error. The fifth requirement was that the system must record the timing of the activity. The verification method we used was testing. The verification we used was method, which was used to demonstrate observing that athlete's input must match the output shown in the debug, along with matching time recorded, a weighted time score is sent to the tablet, measuring the athlete's accuracy. The last requirement is that the system clock must decrement from 3, which results in audio or visual signal. The verification method used was demonstration. We observed results showed an accurate countdown timer and a tone from the tablet. We were able to pass all of the tests, the requirements that we did. We were fortunate enough to have most of our materials donated, which contributed to us staying within budget and having a very inexpensive project.
So in conclusion, our project, we'll get to a demo of this. In conclusion, our project worked pretty well in our state. We had a few, and we encountered a few problems. As in the past few days, we had a few chips let out the smoke on us. So we were able to get past these hurdles and replace everything in time in order to have the full working product with us again today, as we had done in the past. We were able to meet all of the requirements that were set forth to us, and we were able to do it in what we feel is a good product and good design. We were able to get a lot of real-world experience out of this, and we felt that we learned a lot of time management skills. As we all know, we all overestimate how much time we need for each task at hand. So I'm going to bring us to a demonstration of the product itself. So we're just going to get ready our tablet application job for the judges now.
Can you show us the movie
Absolutely. Yep.
before you get started?
Yep.
Volunteering?
Yeah. Does anyone want to do the demo?
There's a lot of ways for me to embarrass myself. That's not one.
Yep. So based on this movie, you're
So much.
yeah, and then if you scroll down, there is the how to write this. If you'd like to select the drop down, you can see all the different drills.
Is that in seconds or milliseconds?
It's in seconds.
What's it, milliseconds? Milliseconds? That was a flash.
Yeah.
That wasn't a human. Oh, sorry, the flash isn't real.
Yep. So I will select a drill. To start off, I'm going to start with the 2-1-2 drill, which begins with the board is facing forward.
Most simple.
Yeah, it's one of the simpler drills.
Okay.
So with the board facing forward towards the audience, with the top here, it will go from the bottom 2, the center 1, the top 2, and reverse down. And
2, 1, 2, 2, 1, 2, 2,
Yep.
1, 2, 2, 1.
as the name suggests. Exactly.
I can sing to that.
So once I select this drill, I'm greeted with the instructions on how to do the drill. So the idea of the drill
It was wild, okay.
Thank you. So you're instructed to do the drill in that correct order 5 times in a row to complete this
So
portion.
who's gonna do it? You? So when I say okay, you.
I will do this drill, yes.
So I'm ready to say okay.
Okay, so if you press OK to that,
Yeah.
I can do it. No problem. So once you press OK to that, it's just going to confirm that that's the drill you want to do. And you'll have the picture below.
It says start drill.
Yeah, we can start the drill.
Ready?
Ooh, boy.
Oh, you don't know, I just changed it. No. Okay, start drill.
So if you press the
Number incorrect, 32.
so I've done it incorrectly.
Waiting time, 31.
Cool.
You don't have to worry about being a high score. That's pretty cool. Good job.
So, let's open up to any questions.